Hello everyone, this is Jean-François Filipot. I'm working for France Energy Marine and I will be presenting with colleagues from the project about offshore wind turbine design, and the results that we will be presenting will be hopefully helping to define new standards for the design of offshore wind turbines exposed to tropical cyclones. And it's a project that we ended recently, about 2025, and that we run with the panel of partners that you can see at the bottom here. So we will have a great panel today. We'll have, so myself, I will be introducing the project. Then we'll have Nicolas Raya will be presenting some new results regarding the statistical description of the tropical cyclone parameters. Then Paul Renaud will make a demonstration of the software that we have designed in the project to assess extreme wind and wave parameters under tropical conditions. And then just Will Hodder from EDF Power Solution, explaining how the result can be used by the industry and what would be the next step to improve further the methods, maybe. Okay, so as I just said, I will be introducing the main result of the project. Then I will have talked by Nicolas about the Monte Carlo approach and the statistics. We will do this presentation of the Typhoon Wave tools. We have the feedback from the industry, some conclusions and next steps. Ask question we like to the comparison tool of it, and we'll try to answer the questions. Okay, so now I jump into the OROWSHI project and a few words about the context. So one of the first motivation of the project was the definition of the standard from the IEC for the design of offshore wind turbine exposed to tropical cyclones. And if you want to follow this recommendation to design your 50 and 500 year wind and wave conditions, you will see that there is two different methods. One for the waves, for the wind, sorry, which is based on the Monte Carlo approach from Ishihara and Yamaguchi, which basically rely on the generation of a very long time period of tropical cyclone, typically 10,000 years of climate with tropical cyclone inside, and it's obviously synthetic data. And the other one for the wave is it's the hindcast-based statistical extrapolation, which is what you use in general at mid-latitude. And the foundation of this is that you use the 25-year, typically 25-year observation database or numerical hindcast that you extrapolate then to get the 500 or 50-year wave condition at your site of interest. And so this comes with at least two issues. The first one is that you will have inconsistencies. You won't have any wind and wave joint statistics because you have the wind values, which is estimated with one method, and the wave value, which is estimated with another one. And this might lead to over-conservative design, because then you will use the worst wind situation plus the worst wave situation together. And the other issue is that it is well known that historical hindcasts are not long enough to capture a sufficiently large number of tropical cyclones. And this can lead to big uncertainties in the extreme wave statistics estimation. Sorry. So what we did in the project was to first try to improve the IEC approach for extreme wind speed statistics estimation, and then we replicated this Monte Carlo approach for the wave parameters to evaluate the joint wind and wave conditions at the return values of interest, which is here 50 or 500 years. So now we'll go through the different results of the project following the work packages here. So we see that there was 6 work packages. The first one, it's about it's about project management. And then we have 5 technical work packages. One about the definition of observational database. Then we worked on improving this IEC method, and we work also on developing a new parametric wind model together with new parametric wave models, because we need a very fast model so that we can then run these Monte Carlo approaches, which requires a lot of tropical cyclone to be simulated. So I'll start with the raw package 2, which is about the creation of a reference database. So we work a lot around this data that we use further than to validate the wind and wave models in the other raw packages. And this is really a key to improve the estimation of the extreme wind and wave statistics, to have enough data that you can qualify so that you can validate the model. So here you have an example of one of the tropical cyclones we studied in the project, which is tropical cyclone Lee, 2023, that cruised along the western Atlantic coastline. So here you have South America and black track. So for instance, the red line are altimeter data. We also have other observation from satellite, including synthetic aperture radar. We also use a lot the Kaya data, which are radars that are embarked in the hurricane hunters, or the aircraft from the NOAA that crosses the eye of the tropical cyclones, and that can give you wind and wave observation really inside. Flight patterns here, it's the track of the flight here that we used. We also use data from cyclones, so small ships, autonomous ships that are deployed also by NOAA, and that gives you access to wind and wave parameters, because they are sailing that can be directed toward the track of the tropical cyclone. We use also drifting buoy, moored buoy from the NDBC. Of course, we use metmast from partners. We use also floating lidars from partners and other instruments. So we learned all this data, how to analyze them, and how to use them for model validation. It was very insightful and really an exciting aspect of the project. Then we move to the next work package, which is about the improvement of the existing IEC method. And so it starts from using parameters from an historical database. Here it's the IBTrax database. From that one, you actually get empirical distribution for the tropical cyclone parameters. It could be the maximum wind speed, could be the reduced maximum wind, for instance, the translation speed of the tropical cyclone. And from this, you try to fit density probability functions. From this distribution, you can draw randomly the parameter of the tropical cyclone and generate wind field above your site of interest. Then you add what we call a speed-up ratio, which accounts for the effect of small-scale orographic obstacle on your site. The hub height, which is typically value at hub height. And so first we implemented the method implemented in the IC, or proposed in the IC, and we also try to improve it. So what we did, and it will be described by Nick, improve this part, the statistical descriptions. We also improved a new parametric surface wind speed. We came up with a utility based on OpenFOAM to compute the speed-up ratio in place of the mascot tool, which is proposed in the IEC and which you have to pay for, and whose manual is written in Japanese. And we also came up with a proposal for vertical extrapolation at hub height. So there is a paper that will be shot out by Nicolas Raya and colleagues, and Nicolas will go into the detail of the result a bit later. And so everything has been implemented in R and in a Shiny app, which is quite handy, and that is available for the partner of the project. Okay, so about the parametric wind field, so we used a new one that we developed in the project, which is based on two different components, one symmetric surface wind model from Loidan and one asymmetric component from Olfert et al. And we combined them together. And let's say that the main novelty is that we adjusted all the parameters of the model using a very big database of synthetic aperture radar observations from satellite, which is currently the best solution if you want to characterize the distribution of the wind field at the sea surface. So the paper regarding this project is now out, and I can send you the reference if you want. Then, as I mentioned, we also worked on the vertical extrapolation using especially data provided by our partners, including RWE and Ørsted as well. And what Paul Renaud showed is that using a logarithmic law with a drag coefficient that accounts from the sea surface properties and the sea surface roughness, following the description or the parameterization by WASP and published in Boin et al., we achieve a better match to the vertical profile of wind speed in a tropical cyclone compared to the power law, which is recommended in the standard document. Then we work on different wave models. So we work on spectral wave models, which are the state-of-the-art wave models, but also they are quite expensive. And if you want to simulate in a Monte Carlo approach the wave field, then you might need, depending on your computational power, you might need lighter models. So we work on two lighter models. One which is super light, it's called the Grossman and Matheson model, recently published. And another one which is, so this one is fully parametric, and another one which is a physical model implemented in a Lagrangian manner that you can use on a laptop here. It's a nice model as well. And here is the workflow that we define and which is first implemented in a Python tool called Typhoon Wave, and it's also a method that we could use for further recommendation for the industry. So that's the method we use to, in the end, obtain a joint statistic of significant wave height and wind speed at hot high. So we start from the storm database, and from this storm database that has been published in Blumendal et al. 2021, which covers 10,000 years of tropical cyclone tracks plus their parameter over the globe. You can access the tropical cyclone parameters. You can compute parametric wind field over the site of interest. Then you can compute the land effect. You can extrapolate at up height. And with the same set of parameters or wind field, you can actually force a wave model. You can force the simplest one, which is Grossman-Matheson here. And from these two components, wind and wave, you can get a joint database of extreme significant wave height and wind speed at up height, which is fully consistent because we use the same database at the beginning, and the wind speed is used to force the wave model. So it's I think it's a nice result. If you want to, if you have the computational power available and you want to go further in detail, you can also use the WaveWatch 3 model. So we derived a specific version with Fabien Leclerc of the WaveWatch 3 model that is adapted to Monte Carlo. It will be published soon as well. Okay, so that's for the tropical cyclone condition only, but as you might know, there might be a background swell that could be sent by another weather system, like a storm that is not directly close to the tropical cyclone. And so we work on the ERA5 database to extract the statistics of the swell that could be below the tropical cyclone. And we add this component as well to the extreme HS that we have here. And another component is that if you are, let's say, in the north of Japan or in the northeast of the United States, then your site might be affected by tropical cyclone during the tropical cyclone season, but also by big storm during the winter storm. So we also extracted the statistics of this extreme storm, winter storm, from the ERA5 database, and we re-injected here on top of the extreme HS computation here. So We can, from this, compute environmental contour, for instance, for significant wave height and wind speed at hub height, and we can also compute univariate values of HS and U at hub height, wind speed at hub height, including the different contributions that I've proposed here. So this is an example of the wind field and wave field we can get with the simplest model for one typhoon in Japan here. And this is an example of the contour for the same site in Japan. You can get if you compute, if you use the storm database as input here. And you can also compute univariate distribution for the wind speed at hub height. And here you have the different contributions. So the blue line is the tropical cyclone contribution only. The orange line is the extra tropical contribution only, the winter storms. And the addition of the two is the green line, or the combination of the two is a green line, which gives you the full extreme values for U150, the wind speed at hub height. And you see that here the site is very quickly dominated by tropical cyclone, above a return period of 2 to 3 years, then everything is dominated by tropical cyclone. And you have the same for the waves here, and you also see that we have added the swells that can be below the tropical cyclone, which is the difference basically between the blue line and the one on the top here. So very quickly, we had many scientific results from this project, and we were very happy that we were able to define a new methodology from this result for joint extreme wind wave statistics under tropical cyclones. And we implemented it in the Typhoon wind wave and the Shiny App software. And so the next step is to publish all the results and to incorporate the methods in certifications and standard document as the one from IEC. So we are now part of the IEC working group that is refining and updating the relevant documents in the IEC. So the timing is very good for us. And we have many papers that I either already published, submitted, or under preparation that we will try to really issue very quickly so that you can contribute to the update of the IEC document.